So, a gentle hi, and today we are going to discuss about the unilateral Laplace transformation of some of the common signals that occur in our circuits. Alright, so first of all, we have seen it before that e to the power minus at u of t. We have seen its bilateral Laplace transformation, but since it is a causal system, so that means its negative, its value on negative time is 0. Its bilateral Laplace transformation and unilateral Laplace transformation are the same, and they are 1 by s plus a. It's our most common signals that occur in our circuits. Alright, and now if I make a 0, that means e to the power 0t, so just ut, then it's going to be 1 over s if I make a 0 also. Ut is simply equals to 1 when t is greater than equals to 0. So for 1 or ut, the unilateral Laplace transformation is simply 1 over s. Next, want to know the Laplace transformation of the Dirac delta. Alright, so Laplace transformation of Dirac delta t by definition is going to be minus infinity to infinity delta t e to the power minus st dt. Now we know delta t minus t naught function of t is simply when evaluated is equals to delta t minus t naught function of t naught. Here t naught is 0, so we put 0 in the place of t e to the power minus st to evaluate it. Okay, so that's the property of evaluation, we know. So it's going to be delta t e to the power minus 0 t dot dt, so it's going to be simply 1, and delta t integration from minus infinity to infinity is also 1, so the Laplace transformation of delta t is 1. Alright, you have to remember that. Now the next obvious thing that occurs always is going to be the sines and cosines. Alright, and we're going to handle that really very easily. So we want the Laplace transformation of, let's say, cosine first of all. Cosine of omega naught t. Alright. Now sine and cosine can be dealt in this form, but it's begging to take it into exponential and asking for real and imaginary part. So cosine omega t is simply the real portion of e to the power j omega naught t. We can exchange the real and Laplace transformation because they are exchangeable, we know. And we also know the Laplace transformation of some exponential. The unilateral Laplace transformation is going to be 1 minus s of j omega naught, remember. And since we know e to the power minus at, the ROC was real part of s is greater than minus a. Now here there is no real portion, it's only imaginary, so real part of s should be greater than 0. 0 is our real part, this is our ROC. Alright, we want the real portion of this, and that will be the our Laplace transformation of cosine omega naught t. So how about we multiply by the complex conjugate all over the in denominator and numerator. So that's going to be s square plus omega naught and s plus j omega naught here, and is going to be s divided by s square plus omega naught square. So that's Laplace transformation of cosine of omega n. And if we want to find out the Laplace of sine of omega naught t, then you can proceed with the same way, but instead of real it's going to be the imaginary, so ultimate answer is going to be omega naught over s square plus omega naught square, where real part of s is greater than minus a. And by the way, um, these two this signal share this ROC of real part of s is greater than minus a. As you explain later on, this signal share the ROC real part of s is greater than 0, because here simply a is equals to 0. And here you see the integral always converts, so here ROC is whole plane. Alright, so we are almost doing it correctly. Almost all the signals are done. Now the last signal we want the Laplace transformation of is t to the power n. Again, referring by Laplace transformation, I am meaning the unilateral Laplace transformation. Alright. and there is a mistake. There should have been 0 here because we are doing unilateral Laplace transformation. We want to derive for delta. Alright, Laplace transformation of t to the power n is equals to 0 to infinity t to the power n e to the power minus st dt. Alright, now this is begging for integration by parts. The people who know some of the shortcuts to do integration of parts will obviously do it in DI method. I ask you to search in internet the DI method of doing integration by parts, as I am going to do that. So obviously the portion that gets reduced is t to the power n, so that's going to be my term that's which I want to differentiate, and e to the power minus st will be the term which I will integrate. So this will be my d and this will be my I. So after first differentiation I get n t n minus 1, and after first integration I get e to the power minus st over s. So my first term to evaluate is going to be t to the power n e to the power minus st over s, and that has to be evaluated from 0 to infinity for t. And then my second integral, because you see in integration by parts there is an evaluation and then another integral, my second integral is going to be the multiplication of these two terms with a minus sign, so that means minus minus cancelled out with plus, and nt n minus 1 e to the power minus st over minus plus s, and the integration is from 0 to infinity. Now when you put 0 here, t will make the terms 0, and when you put infinity here, infinity will make the exponential 0. So this is 0 for all the cases, and this term is simply n by s, the Laplace transformation of t to the power n minus 1. So we can do it in this way, and ultimately the hierarchy will be, for this term we will get n minus 1 over s, for the next term we will get n minus 2 over s, and it will go on till 2 by s, 1 by s for t, and ultimately we will get the Laplace transformation of 1. Alright, so this is simply n factorial over s of n times s, and Laplace transformation of 1 is also another s, as I have said, 1 is ut. So Laplace transformation is of this is also 1 over s, so this is going to be s to the power n plus 1. So these are the 4-5 signals that I always want you to remember the Laplace transformation of: the exponential, the ut, the delta, the cosine, the sine, and the polynomial of t. They are very important in inverse Laplace transformation. They are very important as they occur in our inputs of our systems. Alright, thank you.